Before getting our hands dirty with multiple integration, it's very important to revise some fundamental concepts of the normal integration that you are used to. So let's remember that when we write an integral equals integral sign between limits a and b of a f of x with respect to x, what are we doing? Can you remember? So what we are doing is the following. We have our function f of x as a function of x, which looks maybe something like this. And then we have our two limits, the lower limit a and the upper limit b. And what we are doing is we are calculating the area under this curve. So this area that I shade here, this is equal to the integral I. Now the definition of this integral I was given in terms of a limit. You remember this? This is the Riemann sums. So the integral I is defined as the limit when delta x goes to 0 of the sum of f of xi multiplied by delta x. So let me clarify what everything is with a corresponding picture. So if we plot again our function f of x versus x, so what we did here is, okay, we have the same limits, but what we did is we divided the region into different sections. Okay, and these sections have a thickness or a width given by delta x. Okay, so then we have our function, which is the same function as we had before. Let me try to draw it, similar function. Okay, so then what we do is for each interval delta x, so for example in this first interval we choose a point inside the interval which we called xi. Let me write it, let me move this delta x to another place. Okay, so this point here we call it x1 because it's inside of the first interval, right? So this corresponds to a certain height of the function, and therefore what we draw is a rectangle with a width delta x and a height given by the function evaluated at xi. So this is f of x1. Okay, then we do the same. We look at the second interval and we choose a point inside the second interval, and that is x2. This could be the central point, that is the easiest way to do it, but in fact it could be any other point inside the interval. And then this has a certain width delta x, so we create this rectangle here. And the height of this second rectangle is f of x2. So the function f evaluated at x2. And we repeat this procedure for all of the intervals. And we end up with this structure. And therefore, when we add up the area of these rectangles, and the area of the rectangle is the height, f of xi, multiplied by the width, delta x, and we add up for all of the rectangles, yeah, from I equals 1 to n. So when we do that, we get the area under the rectangles. And in the limit, when delta x goes to 0, these rectangles are made smaller and smaller, so eventually the rectangles perfectly match with the area under the curve. And that is how the integral is defined as a limit. Okay, next, remember this important property of integrals. So, if you integrate a function between a and b, and this function depends, let's say, on 3 variables, x, y, z, and we integrate with respect to x, the result of doing this integral does not depend on x. So the result of this is an integral which depends only on y and z. It does not depend on x. Okay, let me write it explicitly. Or in other words, when you integrate with respect to a variable, this variable disappears. Let me illustrate this with a very simple example. So let me write the example here on the right. let's say you have this function which is a times the exponential of k times x. Okay, so this is a function which depends on three things: a, k, and x. Okay, we could call it xyz, or we can call it akx. It doesn't matter, it's just symbols. So now let's say that we want to do the integral between a and b of this function f of akx with respect to x. Okay, so we are basically doing the integral from a to b of aekx dx. So what's the result? The result is a divided by k times exponential of kx evaluated between x equals a and x equals b. And the evaluation now is the key. So because we are evaluating x equals b and then we subtract the evaluation x equals a, we are getting rid of the x. So we get a over k can be left outside, and we get e to the bx to the kb minus e to the ka. And this is the result of the integral. And this is a function which depends only on a and k. So it does not depend on x anymore. In other words, doing the integral with respect to x got rid of the x dependence. Okay? So that's what I mean by this. Now there is a kind of exception to this rule, and that's when the limits include x. So what if the limits include x? What if you try to evaluate an integral which is a function of f of x dx, but now the limits are from a to x? And what happens now is that we can get confused. Although this notation is used very often, it's actually a bit confusing because this x is not the same as this x, right? So if we want to be strict, I would call this x prime. Okay, so we are integrating f of x prime dx prime between a and x. Okay, so what does this mean if we draw what this integral means? So we have our function f of x versus x, and we have whatever we have. And we have a fixed starting point, a, but then we are calculating the area between a and an arbitrary point x. Okay, so we can have a point x, but this point is moving to the left or to the right, depending on which x we choose. Okay, so this is a moving point, and we are calculating the area in this region. But of course, if we change x, the area will change, right? So this area is the integral, which is a function of x. So therefore, I could write here that this integral is a function of x. So this time, doing an integral with respect to x still leaves you with a function that depends on x. And it's all thanks to the fact that x is in the limit. Okay? And this will be very important to understand multiple integrals.